Good evening, dear students and my dear parents who are watching this program. My teacher, which is the live classroom of the UAE. So, I wish to welcome you all for this program. Today, it's a live session of basically meant for grade 12 students. So, those who are watching this program, so you can request the students of grade 12 to watch this, especially those who are doing science. We are discussing some concepts on the first unit of the physics portion of grade 12. So, that is basically main focus will keep on the device called capacitors. The last two sessions we were dedicating to the calculation based concepts, that is by making use of logarithms. How calculations can be done, that is what we were discussing last 2 weeks. So, I hope you had seen those sessions for how to solve numericals using logarithms. But today, we will right away get into some contents of grade 12 physics. You know, in this year, you are going to have serious practical lessons. For the examination, you are supposed to do 15 experiments, 5 activities and some project works, investigator projects and all. So, one of the activities which you are going to do is identification of components. You may have to identify some components, electronic components, and you will be studying a lot of components this year. One of the components we are doing is capacitors, or we are learning about is capacitors, which you do in the first unit itself. See, you should be familiar with the electronic components. I will show you a few components of which we will discuss about capacitors. See, this is a circuit board, you must be familiar with these kind of boards. Okay, most of the electronic circuits you can see the components like this, right. That means it is like this is, you can say it is a capacitor. This is what we are discussing about. Okay, we will discuss the concepts of capacitors. So, this is a capacitor, and you know this is a transistor. The black one is transistors, and these are the carbon resistors, which you might have done in current electricity lesson. These are the carbon resistors with color codes. So, carbon resistors, and we know you must be familiar with this one. These are LEDs. Okay, so I showed you 1, 2, 3, 4 components. Okay, the capacitors, resistors, LEDs and transistors. Okay, so these we were studying about these components. All these components we will have to study this year. Out of this, we will talk about capacitors today. Today's session we will have on capacitors, right. So, I hope all of you have seen these components. This is one of the components. What I have shown over here is capacitor, that is we will discuss today. And more focus we will give on numerical problems based on capacitors. So, for which you should know a few points about the capacitors. So, basic equations we have got in capacitors. You know how much charge is stored in a capacitor? Basically, the capacitor or condenser, it is also called condenser. It is a device for temporary storage of charges in electronic circuits. If charges are stored, what else we can say is there will be storage of electrostatic energy. Energy will be stored in it, right. So, how much charge is stored in a capacitor, that purely depends on how much potential difference is applied to it. So, we may say Q proportional to, directly proportional to V, or Q is equal to a constant times V. This constant is what is normally referred to as capacitance. Okay, so, this is capacitance. So, the unit of capacitance is what is, the SI unit is what, farad. Whereas the farad is a big unit. SI unit of farad, SI unit of capacitance, farad is a big unit, and that is why commonly we use units like microfarad, picofarad, nanofarad and all. Okay. So, you are familiar with this equation Q, where Q is the charge, C is capacitance and V is the potential difference supplied. Further, let us see what are the factors on which capacitance of a capacitor. Basically, the term capacitor you can even compare with what we have studied in resistors. You know, resistor has resistance. Similarly, capacitor has capacitance. resistor we are well familiar with, no, V is equal to IR and R. All right. So here Q is equal to CV is the equation which we use for the calculation of the charges, charge stored in a capacitor. C is what is called capacitance, and the unit of C is, or capacitance, is farad. Okay, so but if it is in microfarad and all, you will have to convert it into standard unit farad. Like micro stands for 10 to the power minus 6, and if it is picofarad, should convert it into farad by multiplying with 10 to the power minus 2. Sorry, minus 12. Okay, 1 picofarad is 10 to the power minus 12 farad. Okay. So now let us see the factors that can influence the capacitance of, for a given, I showed you the capacitor, for a given capacitor, it has got a given capacitance. So it depends on these many factors. So next equation you should be familiar with is C is equal to epsilon 0 A by D. So of this, C stands for capacitance, epsilon 0 is a physical quantity, what is called as permittivity of free space, O, epsilon naught, that 0 stands for free space. Okay. So C is capacitance, epsilon naught is representing the permittivity of free space, A represents the area of the plates which we use in capacitors, and D is the separation between the plates. In fact, in a capacitor there should be two metallic plates, and they should be separated by a distance D. This is the case of capacitor. So A is the area of the plates and D is the separation between the plates. Different types of capacitors we have. Okay, of different types of capacitors, how do we classify the capacitors? We have capacitors in almost every electronic circuits, especially in radio tuner. One of the applications for capacitors is radio tuning of radio. Tuning, in the receiver, we are doing the process of tuning, that is with the help of capacitors. And even we have in filter circuit, modulator, demodulator, many different electronic circuits we have the use of capacitors. Okay, so in every capacitor there should be some metallic or two metallic plates, but the plates can be of any shape, maybe parallel plate, maybe it may be a cylindrical one, maybe spherical, according to what's the shape of the metallic thing which we use as plates. We have different names like parallel plate capacitor, spherical capacitor, cylindrical capacitor and all. But as per the syllabus, we are going ahead with parallel plate capacitors, that is two metallic plates like this and separated. What is there in between? Between the two plates there is a dielectric. It's a dielectric medium, that is there are medium with no free electrons. Okay, here according to this equation we have, this is nothing but free space, okay, vacuum. Okay, but it can be filled with some materials. If you fill with some material, what happens is permittivity will change. It will have another permittivity. Maybe its permittivity is higher than, always it is higher. Suppose you are filling it with oil, some kind of oil, if you fill it with, we can say its permittivity increases, thereby capacitance will increase. So that means, how do we make a capacitor with a high capacitance? If you want a capacitor of large capacitance, what do we do for that? First, we can use a plate of large area as possible. Second, we will keep the distance as close as possible, right? And third one, you fill it with a material which has got a high permittivity. That is why sometimes we use, paper, ordinary paper is used as the dielectric medium between the plates. That is called, so depending upon what's the type of dielectric we are using, what's the type of medium we are using, we have different types of capacitors again. Okay, the dielectric we are using is, like if it is paper, we say paper condenser or paper capacitor, and we have mica capacitors. So depending upon the nature of the dielectric, depending upon the the shape of the plates, we have different classifications of capacitors. All right, that's about capacitors. Okay, so for the time being, you remember these two equations. One is Q is equal to CV, the other one is C is equal to epsilon 0 A. So now you can have a look at the screen. So you'll see that the capacitor, you can see the plates of the capacitor. Okay, so the plates are separated. Okay, so that is here I'll show you. Okay. All right. So this one you can very well see it on the screen. That it is, yeah, you can watch it now. See, if you adjust the capacitor value, capacitance, see this is how we adjust the distance between the plates. So, we can see on the screen a battery connected to a plates, but battery 0 volt only is what is supplied. All right. So, now if I increase the voltage, you can see one thing. See, if I am supplying 1.5 volt, you see how much charge is stored over there. So, this is positive, it is negative. So, there is an electric field set up between the two plates. All right. So, I will show you the capacitance value. You can make out from this one 0.3 times 10 to the power minus 12 farad is the capacitance of this one. That depends on the plate's area according to the equation I showed you. That depends on the plate area and the separation between the plates. Okay. So, it has got plates charge, this is the charge, Q is equal to CV. So, what do you understand is, if you increase the separation, what do you observe? If you increase the separation, capacitance decreases. See, when D increases, capacitance decreases. See, it is inversely proportional to D, right? That is what you understand, all right. Now, you see what happens if you increase the area. So, when you increase the area, see capacitance increases, thereby the charge also increases. So, that is what you understand from this picture or from this simulation, all right. This is battery providing charge on this, and charge causes electric field. You can even see the electric field value. So, this is called electric field detector. You can see this is 206 volt per meter is the electric field existing in this direction from positive to negative. And also we have got an equation for the stored energy. I think you remember the equation for stored energy. See, just see the equation I will show you. The energy U is equal to half CV squared, or energy is equal to Q squared by 2C. This is another equation we have. So, these two equations are useful for calculation of energy. Okay, so, that energy value also you can see in the next meter. You can see the yellow bar in this on the screen, that is indicating the total energy stored. See, here you can see this is the total energy stored, that is indicated by the yellow bar. The red bar indicates the plate charge and the green bar indicates the capacitance. You just see what happens when you change the voltage. See, I am changing the voltage. You can see when I decrease the voltage, charge decreases and even energy also decreases. But what do you say about the capacitance? What do you see about the capacitance? Capacitance does not change, because capacitance depends only on area, distance between the plates and nature of the medium between the plates. Okay, so, I will just show you the electric field lines as well. You can see the lines, electric field lines are acting from positive to negative. This is the direction of electric field lines. You can see from positive to negative. But just observe one more thing. If you decrease the if you increase the separation, see, I am increasing the separation. You see the changes happening over there. All the three change, right? If you increase the separation, the capacitance decreases, right? Charge thereby decreased, and even energy also is decreased. Look at the value of electric field here. In that also decrease. It becomes, see, before it was 106, now it has become 72 volts per meter. Okay, now another thing I will show you is just look at the on the screen again. You can see what happens when a dielectric slab, this is a dielectric slab. When a dielectric slab is inserted between the plates of the capacitor, what exactly is happening? You can look at that. Okay, just watch it carefully. So, I am increasing the voltage here. See, the voltage is increased to some value. Okay, accordingly, there is electric field developed here. See, I will just show you electric field as well again. See, this is the electric field detector, that is in between, there is electric field. You can see one thing, this line, this vector 93 volt per meter marked over here, that indicates, so I will keep it here. Okay, all right. So, this is indicating the value of the electric field acting downwards between the plates of the capacitor, right? And that itself, see, this green line is what is indicating the total electric field. Total, when you say there is nothing else is acting, only 93 volt per meter, that only is what is total as well. And inside the dielectric you can see 0 volt per meter, nothing is there. Why? Because it is outside. Okay. Now, let us just observe what is happening when it is brought closer and closer towards it. See, it is brought closer, and what do you observe here? It starts, see, one thing very clearly, if you closely observe, one thing you can see is, so before that let me tell you one more thing. Inside the dielectric there is a, it is neutral, positive, negative together they remain. Now, just closely observe and see what is happening inside the dielectric, inside this slab when it is moved into it. You see, when it is taken into the plate, see, the negative goes towards that. Have you seen that? The blue line goes up. Okay? That means the negative is coming closer to the positive plate. So what happened is there is another this also we can make out. You see, this yellow line now it has come, right? This is what this yellow line, that is the electric field newly developed inside the dielectric slab. You know, inside the dielectric slab there is an induced electric field. That induced electric field is what is represented by this yellow line, and this line represents the electric field already present over here. Okay, that is from positive to negative. Downwards there is an electric field that is indicated by this line, whereas on the dielectric slab it is indicated by the yellow line. So what is exactly the sum, vector sum you have to take, this minus this, all right. So this green one, that represents the net electric field. So what is exactly happening from according to this description, what you can write is, when a dielectric slab is inserted between the plates of a capacitor, the overall electric field inside the slab becomes less. You see, initially if dielectric slab was not there, whatever the electric field, 93 volt per meter, 93 volt per meter here also, 0 is inside the dielectric. Okay, this was the total. But when it is kept inside, what happens is there is 467 volt per meter is the electric field here, new high electric field, but that is opposed by this one. So electric field here decreases. Okay, so total electric field inside the dielectric slab decreases due to the insertion of the dielectric slab. That's what we understand. See, even electric field lines you can see on the figure. All right, so this is the concept about even stored energy and all. See, this is energy stored. All these we can even represent over here as well. All right. So the next thing what I want to tell you is, it's about the capacitor, what's happening to the capacitance, what are the factors affecting capacitance, and what happens when a dielectric slab is inserted between the plates of the capacitor. These are the areas I already explained. All right. Next thing what we're going to see is, you know, like you're familiar with the combinations, you know, like resistors connected in series, you might have studied, like that even capacitors also we can combine them. So very important aspect to understand is, if the capacitors are connected in series, you know, one after the other, series connection means like the plates are connected in this way. So the internally only connection comes, the other exterior plates are, or the other two sides the plates are connected to outside, only these two are connected to the battery. These plates are internally connected. This kind of connection is series connection, right? When you connect the capacitors in series, the effective capacitance is given by an equation 1 by Cs is equal to 1 by C1 plus 1 by C2. This is an equation to be used to calculate the effective capacitance. By the way, this effective capacitance is given by this equation. So most of you make mistakes over here, how you will not take the reciprocal for finding the final answer. So this is the point where you have to be very careful about, because at this point if you are finding, see, usually what you will write is the effective capacitance is equal to 1 by C1 plus 1 by C2. That is wrong. But what you should say is 1 by effective capacitance. Otherwise, the reciprocal of effective capacitance is the sum of the reciprocals of the individual capacitances. So you calculate 1 by C1 plus 1 by C2, and at the end you have to take the reciprocal as well, right? That's about series connection. And in parallel connection instead, if the capacitors are connected in parallel, the effective capacitance is given by Cp is equal to C1 plus C2. That is, parallel connection means it will come like this. See, both the plates are connected together in this way. Okay, so the plates are connected together over here. This is the, see the two plates C1 and C2 connected like this. Okay, this is what's the case of parallel connection. All right, that is parallel connection. This is series connection. Okay, parallel and series shown here. Okay, in parallel connection, the effective capacitance is what? Sum of the individual capacitances, and in series connection, the effective capacitance is given by the equation 1 by Cs is equal to 1 by C1 plus 1 by C2. So that's one thing to understand. Okay, so an aspect to understand carefully is, in parallel connection, once again let me tell you about it. In parallel connection, the just add the values of the capacitance, that will give you the total capacitance. Right, so that is maybe 2 microfarad, 3 microfarad, 5 microfarad. If they are added together, you will get 10. So that value of 10, that is the effective capacitance what we are getting in parallel combination, will always be greater than the highest highest capacitance. See 1, 2, 3, or 1, 3 or 2, 3, 5. If it is taken like that, so the greatest one is 5. So total capacitance what we are getting is even greater than 5. Whereas in series combination, it's the other way. since it is reciprocal of the effective is what is the sum of the reciprocals of the individual capacitance values. So, from that what we can understand is, if two capacitors are connected together or three capacitors are connected together in series, the effective capacitance will always be lower than the lowest of the individual values. That is the important aspect to understand. The effective capacitance is always lower than the lowest of the individual values. That is the case of series combination. Actually, this fact is useful, very much useful when you do the numerical problems. In numerical problems, what happens is, like, you can verify the answer, and if the question is to calculate the effective capacitance either in series or in parallel, you can make it like this. If it is series, you just check the final answer. If the answer comes to be lower than the lowest of the values, that is correct if it is series combination. Whereas, if the answer is higher than the highest of the individual values of the capacitors, that is what is exactly required for parallel combination of capacitors. Alright, this is something to understand carefully. Now, with this note about the capacitors and the introduction of the dielectric slab, one more point I want to tell you is, when a dielectric slab is completely filled inside the conductor, inside the capacitor, what happens is the capacitance will always increase. How many times? There is a constant called dielectric constant. Say for example, if it is oil may have some dielectric constant, that will be like if K is the dielectric constant of a substance. So, to understand the concept this way, the value of the dielectric constant, if it is K, the capacitance will always be K times the original. Understood? That means, when a dielectric slab is completely inserted between the plates of the capacitor, that is, between the plates of the capacitor is completely filled with the dielectric of dielectric constant K, the capacitance becomes K times the original capacitance, K times the original. Okay, so, this is what is required for solving some numerical problems. Right. From this, actually we have a definition of dielectric constant also. We can write K is equal to C by C0. So, there may be a question, define dielectric constant in terms of capacitance. So, what is the definition of dielectric constant in terms of capacitance? Dielectric constant is defined, I will tell you the definition based on this equation. Okay. Dielectric constant is the ratio of the capacitance of a capacitor with the dielectric between the plates to that of the same capacitor without the dielectric between the plates. Right. Once again, let me tell you the definition. Dielectric constant of a medium is the ratio of capacitance of the capacitor with the dielectric between the plates to that of the same capacitor without the dielectric. This is the definition of dielectric constant. Alright. So, now I will show you one more simulation from this. You can see about multiple capacitors. It means, when capacitors are in series or parallel, how are they connected? I will show you that. Just have a look at the screen. See, this is just one capacitor connected without any battery voltage. So, now if I am applying battery voltage, this is the case. Okay, capacitance, you can, when I increase the value of capacitance, we are decreasing the distance. This is what is the value given. Whereas, in the case of series combination, you can see this is two capacitors connected in series. So, total capacitance will be, you see what is the total capacitance, this is total capacitance. So, you can, one thing we can make out from this, the value of this capacitance is given to be 1 times 10 to the power minus 13. See, from the screen you can make out, and the other one also same thing, 1 into 10 to the power minus 13. But when you connect them in series, what do you observe over here? It is just becomes half. So, two capacitors of equal capacitance when connected in series, the effective capacitance becomes half the original. That is, half the original means like it is 1, now it becomes 0.5. How about if you connect 3 capacitors in series? See, these 3 capacitors in series. Now, what you observe is, just it becomes 1/3, total capacitance becomes 1/3 of the original. So, single capacitor 1.2 into 10 raised. So, capacitance, see, when I am connecting them in series, the total capacitance decreases, that you can make out from this one, total capacitance decreases on connecting in series. Now, we just observe the case of parallel combination. Now, this is the case when two capacitors are connected in parallel, 1, 1. So, it is 2 times 10 to the power minus 13 is the total capacitance, just addition. How about if, say, I will zoom again this way. So, it is 0.2 times 10 to the power minus 12 otherwise. If 3 in parallel means again it will increase. So, this is how you connect capacitors in parallel, 3 capacitors in parallel. So, now in the other picture you can see these two capacitors are in series, that is in turn connected in parallel to the third capacitor. See, this is the case, these two capacitors are in parallel and the third one is in series with that. So, accordingly the values you can calculate So, a point very clearly you should be aware of is the about capacitance. Okay, the charge in every capacitor in series combination, this is something which you have to clearly understand, because next session we are going to discuss some numerical problems. Okay, before that let me tell you, in a series combination all the capacitors will possess the same quantity of charge. So, whatever charge you calculate as a total charge taken from the battery, that itself would be the charge of each capacitor. That is something to understand. Okay, charge is the same everywhere in a series capacitor, or capacitor is in series. Whereas in parallel combination, voltage is the same, potential difference is the same. So, according to what is the capacity, the charge, it will store charges. So, charge will be different, but potential difference will be the same. Okay, so with this note we will move on to a short break. After the short break we will discuss numerical problems. So, you have to stay tuned, and if you have any numerical problems, doubts, you can keep with you and you can call and ask the doubts related. Especially we will focus on the first unit, that is electrostatics. If any confusions there, if you have, you can very well call us, and it's a live program. So, anyway, we will go for a very short break and we will come back for numerical problems on electrostatics. Stay tuned.